Today we are going to talk about RLC series circuit. We apply an AC voltage across the series combination of resistor, inductor and capacitor. There will be a time varying current in this series circuit, and this time varying current results in a voltage drop across the resistor, a voltage drop across the inductor, and a voltage drop across the capacitor. So there will be an AC voltage across the resistor that is represented by VR. There will be an AC voltage across the inductor which is represented by VL, and there will be an AC voltage across the capacitor which is represented by VC. If we apply KVL to this loop, according to KVL, the voltage across the source will be equal to voltage across the resistor plus voltage across the inductor plus voltage across the capacitor. So the sum of the voltage across all these three passive circuit elements results in the source voltage. We assume that the current in this series combination is known, and on the basis of this current we are going to find out the voltage across the resistor, the voltage across the inductor, and the voltage across the capacitor. We have already discussed the equation for the voltage across the resistor in the previous topics. Similarly, we have discussed the voltage across the inductor in the previous topics, and we have discussed the voltage across the capacitor in the previous topics as well. So it will be very easy for us in this particular class to discuss the AC voltage across the resistor, AC voltage across the inductor, AC voltage across the capacitor, and AC voltage across the source. So we consider the equation for the AC current. We know that the AC current in this series combination is equal to Im sin omega t. So this is the equation for the time varying current in this series combination, where Im represents the maximum value or the peak value of this AC voltage. So here is the maximum value or the peak value of this AC current, not AC voltage, AC current. Omega is the angular frequency of the AC voltage source, and we know that omega is equal to 2 pi f. So we can find out the angular frequency of the AC voltage source with the help of this equation. So we know the equation for the AC current in this series combination, and we consider the waveform for the AC current in this series combination. This is the waveform for the AC current in this series combination, and you see this AC current varies with respect to time. This is how the AC current varies with respect to time in this series combination. So we know the equation for the AC current, and on the basis of this equation we are going to find out the voltage across the resistor. So let us discuss the voltage across the resistor. We can find out the voltage across the resistor with the help of Ohm's law. The voltage across the resistor will be equal to IR. So what we do, we put the value of the AC current in this equation, and we get the equation for the AC voltage across the resistor. The voltage across the resistor will be equal to IMR sin omega t. So you see, the phase angle of the current is 0, and the phase angle of the voltage across the resistor is 0 as well. So we can say that the voltage across the resistor is always in phase with the current. The current is in phase with the voltage across the resistor. There is no phase difference between the voltage across the resistor and the current. These two quantities are always in phase. So the voltage across the resistor is always in phase with the current. Here is the waveform for the AC voltage across the resistor. We have taken omega t along x-axis and the AC voltage across the resistor along y-axis. Here is the maximum value of the AC voltage across the resistor, and this maximum value takes place at omega t is equal to pi by 2. So this is the waveform for the AC voltage across the resistor. You know how to find out the voltage across the resistor. You have the equation, and you can find out this voltage with the help of this particular equation. Now we talk about the voltage across the inductor. So the voltage across the inductor can be calculated with the help of L di by dt. So if we put the value of the current in the first equation, we get the voltage across the inductor, and the voltage across the inductor will be equal to Im XL cos omega t, where Im indicates the maximum value of the current, XL represents the inductive reactance of the inductor. This is the inductive reactance, and this inductive reactance opposes the flow of AC current. So the maximum value or the peak value of this AC voltage is represented by VLM, which is equal to the maximum value of the current multiplied by XL. So this quantity represents the peak value or the maximum value of the AC voltage across the inductor. And we know that cos of omega t is equal to sine of omega t plus 90 degree. So the phase angle of this voltage is 90 degree. As the phase angle of the current is 0 and the phase angle of this AC voltage is plus 90 degree, so we say that the voltage across the inductor leads the current by 90 degree. In other words, the current in an inductor lags behind the voltage across the inductor by 90 degree. In other words, there is a phase difference of 90 degree between the voltage across the inductor and the current. So the phase angle of the current is 0, and the phase angle of the voltage across the inductor is plus 90 degree. So the voltage across the inductor leads the current by 90 degree. We consider the waveform for this AC voltage. So we take omega t along x-axis and the AC voltage across the inductor along vertical axis, and here is the waveform for the voltage across the inductor. We consider one complete cycle of this AC voltage, and this AC voltage is shown from omega t is equal to minus pi by 2. So you see in this waveform that the voltage across the inductor leads the current by 90 degree. So we can find out the voltage across the inductor with the help of this equation. We will use this equation in numerical problems to find out the AC voltage across the inductor. Now we are going to discuss the AC voltage across the capacitor. We can find out the AC voltage across the capacitor with the help of this particular equation. So the voltage across the capacitor is equal to 1 over C, the integral of I dt. So what we do, we put the value of the AC current in the first equation, and we integrate this current with respect to t, and we simplify the equation for the voltage across the capacitor. So we get the voltage across the capacitor. Here is the AC voltage across the capacitor. In this particular equation, the maximum value of the current is represented by Im. Xc is the capacitive reactance of this capacitor, which depends upon the frequency as well as the capacitive reactance of the capacitor. So when the frequency is 0, the capacitive reactance will be equal to infinity. The capacitor will block the DC current. We can reduce the capacitive reactance of the capacitor either by increasing the frequency of the source or by increasing the capacitance of the capacitor. We know that sine of omega t minus 90 is equal to cos minus cos of omega t. So sine of omega t minus 90 is equal to minus cos of omega t. So if we compare this equation with the equation for the AC current, you see the phase angle of the AC current in this series combination is 0, while the phase angle of the AC voltage across the capacitor is minus 90 degree. So we say that the voltage across the capacitor lags behind the current by 90 degree. In other words, the current in the capacitor leads the voltage across the capacitor by 90 degree. In other words, there is a phase difference of 90 degree between the voltage across the capacitor and the current. So you see the maximum value of the voltage across the capacitor is represented by VCM. So this is how we represent the maximum voltage across the capacitor. The maximum value of the voltage across the capacitor is equal to Im, where Im indicates the maximum value of the current in this series combination multiplied by Xc, where Xc is the capacitive reactance of the capacitor. So this is how we calculate the maximum value or the peak value of the AC voltage across the capacitor. If we divide this maximum value by under root 2, we get the RMS value of the AC voltage across the capacitor. Anyhow, we consider the waveform for the AC voltage across the capacitor. So we consider one complete cycle of this AC voltage only. You see this AC voltage starts from omega t is equal to pi by 2, and this voltage is lagging behind the current by 90 degree. Now we are going to find out the equation for the AC voltage across the source. So we already know that the source voltage, which is an AC voltage, is equal to the AC voltage across the resistor plus the AC voltage across the inductor plus the AC voltage across the capacitor. So the sum of all these three voltages results in the voltage across the source. And what we do, we put the value of the voltage across the resistor in this equation, the value of the voltage across the inductor in this equation, and the value of the voltage across the capacitor in this equation. And if we put the values of these three voltages on the right hand side of this equation, we get the voltage across the source. So the voltage across the source is equal to IMR sin omega t plus IMXL cos omega t minus IMXC cos omega t. We can write down the same equation in this format as well. In this format, XL minus XC is known as the net reactance of this series combination. This is the net reactance which is offered by the inductor as well as capacitor to the flow of AC current. So this is how these two passive circuit elements oppose the flow of AC current. X is known as the net reactance of the inductor as well as capacitor, and the net reactance will be equal to XL minus XC. We can find out the equation. We can find out the voltage across the source with the help of this particular equation. We can put the value of the time on the right hand side of this equation, and we can find out this voltage at any point of time. This is an AC voltage across the source, and we know that an AC voltage has a maximum value, so it's very difficult to find out the maximum value of the AC voltage from the right hand side of equation number 3.70. Similarly, there is a phase angle of the AC voltage. You see, if we look at all these equations, the phase angle of the voltage across the resistor is 0. The phase angle of the voltage across the inductor is plus 90 degree. The phase angle of the voltage across the capacitor is minus 90 degree. So this AC voltage will have a phase angle. This phase angle might be 0, it might be 90 degree, or it might be less than 90 degree and greater than 0. So we can find out the voltage across the source with the help of this particular equation at any point of time, but this equation does not give you the maximum value of this AC voltage and the phase angle of this AC voltage. So this is the only problem at the moment with this particular equation. So what we do, we consider the general equation for the voltage across the source. This is an AC voltage, so this AC voltage will be equal to Vm sine omega t plus minus theta. I will explain this plus minus sign with this angle. There will be three different natures of this series combination. If theta is 0, then this series combination will behave like a resistive circuit. If theta is positive, then this series combination will behave like inductive circuit, and if theta is negative, then this series combination will behave like capacitive circuit. So anyhow, the nature of this series combination depends upon the value and plus and minus sign with theta. If theta is 0, the entire series circuit behaves like a resistive circuit. If theta is positive, then the entire circuit behaves like inductive circuit, and if theta is negative, the entire circuit behaves like capacitive circuit. Anyhow, this is the general equation for the source voltage, we need to find out the peak value or the maximum value of this AC voltage, and we need to find out the phase angle of this AC voltage. So what we do, we replace the series combination of these three passive circuit elements by a single passive circuit element. If you look at this series circuit, there are three passive circuit elements in this series circuit. The resistance of this passive circuit element is R. The opposition offered by the inductor to the flow of AC current is known as inductive reactance, which is represented by XL, and the opposition which is offered by the capacitor to the flow of AC current is represented by XC. So we have got the series combination of these three passive circuit element in the original circuit, and what we do, we replace the series combination of these three passive circuit element by a single passive circuit element. We represent this single passive circuit element by a box, and the resistance of this single passive circuit element is represented by Z. We assume that the resistance of this single passive circuit element is equal to the impedance of this series combination. You see, what is impedance? Impedance is the total resistance which is offered by the series combination of these three passive circuit elements to the flow of AC current. So we assume that the resistance of this single passive circuit element is equal to the impedance of this series combination. So we replace the series combination of these three circuit elements by a single circuit element, and we apply the same voltage across this single passive circuit element. The same current flows in this single passive circuit element. There is no difference between the current of this circuit and the AC current of the original circuit. You see, there are three passive circuit elements in the original circuit. So we apply KVL to this particular loop. According to KVL, the voltage across the source is equal to the voltage across this passive circuit element. It is equal to the voltage across this box. So the maximum value of the voltage across the source will be equal to the maximum value of the voltage across this single passive circuit element. We know that the maximum voltage across the resistor is equal to IMR. So if you know the maximum value of the current in the resistor and the resistance of the resistor, we can find out the maximum voltage across the resistor. Similarly, the maximum voltage across the inductor is equal to IMXL. So if we know the maximum value of the current in the inductor and the inductive reactance of the inductor, we can find out the maximum voltage across the inductor. Similarly, the maximum voltage across the capacitor is equal to the maximum value of the current multiplied by the capacitive reactance. So if we know the maximum value of the current in the capacitor and the capacitive reactance of the capacitor, the product of these two quantities results in the maximum voltage across the capacitor. Similarly, if we know the maximum value of the current in this single passive circuit element and the resistance of this single passive circuit element, we can find out the maximum voltage across the source or the maximum voltage across this single passive circuit element. So the maximum voltage across this single passive circuit element will be equal to the maximum value of the current in this single passive circuit element multiplied by the resistance of this single passive circuit element. The resistance of the single passive circuit element is represented by Z, where Z is the impedance of the original series circuit. So we can find out the maximum voltage across the source with the help of this particular equation. So what we do, we put the value of Vm in equation number 3.71. Here is equation number 3.71, and we put the value of Vm in this particular equation, where Vm is equal to the maximum value of the current multiplied by the impedance of this series combination. So let us put this value of the maximum voltage in equation number 3.71. If we put this value in equation number 3.71, we get equation number 3.72, the maximum value of this source voltage is IMZ, where Z is the impedance of this series circuit. So the source voltage is equal to IMZ sine of omega t plus minus theta. If theta is 0, the circuit behaves like a resistive circuit. If theta is positive, the circuit behaves like inductive circuit. If theta is negative, the circuit behaves like capacitive circuit. So what we do, we expand sine of omega t plus minus theta. We know that sine of omega t plus minus theta is equal to sine of omega t cos of theta plus cos of omega t sine of theta. So we expand the previous equation, and this is the AC voltage across the source. The AC voltage across the source is equal to IMZ cos theta sine omega t plus IMZ sine theta. You see, let us consider another equation for the source voltage. We have already derived, you see, this particular equation. Let me consider the equation over here. We can find out the voltage across the source with the help of equation number 3.70 as well. So I consider this equation and this equation. So you see, the voltage across the source is also equal to this voltage is also equal to Im R sine omega t plus minus Im XL minus XC cos omega t. So we can find out the source voltage with the help of this particular equation as well. And if you compare these two equations, you see R in this particular equation is equal to Z cos theta, and XL minus XC in this particular equation is equal to Z sine theta. So R is equal to Z cos theta and XL minus XC is equal to Z sine theta. So if we compare these two equations, we get R is equal to Z cos theta and XL minus XC is equal to Z sine theta. So what we do, we take the square on both sides of these two equations and we add them. If we take the square on both sides of these two equations and if we add them, we get R square plus XL minus XC whole square, which is equal to Z square. Why? Because cos square theta plus sin square theta is 1. So we can find out the impedance of this series combination with the help of this equation. So you see the last equation shows that Z, which is the impedance of this series combination, will be equal to under root R square plus XL minus XC whole square. So we can find out the impedance of this series circuit with the help of this equation. Similarly, if we divide this equation by this equation, then we get tangent theta, and tangent theta will be equal to XL minus XC divided by R. So tangent theta is equal to XL minus XC by R, and we can find out the phase angle of the source voltage with the help of this particular equation. So theta can be calculated with the help of this particular equation. So you see, if XL is equal to XC, then theta will be 0, and the entire circuit will behave like a resistive circuit. This series combination will be under resonance condition. Under resonance condition, the impedance of the series combination is minimum, the current in this series combination is maximum, and the circuit behaves like a pure resistive circuit. So if XL is equal to XC, this circuit will be under resonance condition. The circuit will be known as resistive circuit. The phase angle will be 0. The current will be in phase with the applied voltage. If XL is greater than XC, then theta will be positive, and if theta is positive, then the entire circuit will behave like inductive circuit. Similarly, if XL is less than XC, then theta will be negative. This theta will be negative, and the entire circuit will behave like capacitive circuit. Anyhow, there are three different natures of this series combination. It might behave like a resistive circuit, inductive circuit, or a capacitive circuit. You see, we have already discussed these equations. This is how we calculate the power which is taken by the resistor from the AC voltage source. This is the instantaneous power. We can find out the value of this power at any point of time, at any value of time. This is how we calculate the power taken by the inductor. This is the time varying power which is taken by the inductor from the AC voltage source. Similarly, the time varying power which is taken by the capacitor from the AC voltage source can be calculated with the help of this equation. So you guys can calculate the time varying power taken by the resistor with the help of this equation, the time varying power which is taken by the inductor from the AC voltage source with the help of this equation, and this is the power which is taken by the capacitor from the AC voltage source. So according to the law of conservation of energy, the power supplied by the source will be equal to the power taken by the resistor plus the power taken by the inductor plus the power taken by the capacitor. We obtain this equation in accordance with the law of conservation of energy. The law of conservation of energy states that the power supplied by the source will be equal to the power taken by the entire circuit, and the power taken by the entire circuit will be equal to the power consumed by the resistor plus the power taken by the inductor plus the power taken by the capacitor. So we can calculate the total power with the help of, you see, these equation. So if we put the values of PR, PL and PC in this equation, we can calculate the total power which is taken by the entire circuit, or which is supplied by the voltage source, with the help of equation number 3.77. So you guys can calculate the total power supplied by the source with the help of equation number 3.77. We consider the average powers. So the average power supplied by the source will be equal to the average power taken by the entire circuit, and the average power taken by the entire circuit will be equal to PR plus PL plus PC. We know that the average power taken by an inductor from the AC voltage source is 0. The inductor does not consume any power under ideal condition. Similarly, the average power taken by the capacitor from the AC voltage source is 0. These two are energy storing elements. The inductor stores the electrical energy in magnetic field, and the capacitor stores the electrical energy in its electric field. So as the power taken by the inductor is 0 and the power taken by the capacitor is 0, so the power which is taken by the entire circuit will be equal to I square R, or the power which is supplied by the source will be equal to I square R. So this is how we calculate the voltage across the resistor, the voltage across the inductor, the voltage across the capacitor, the voltage across the source, and you guys can calculate the total power supplied by the source as well. Thank you so much. We will do the numerical questions in the upcoming class.